So in this booklet, we will look at the electromagnetic induction questions. Number one, why we transmit electric power at very high voltages? Because it minimizes power loss, because the power loss is linked to I square R. I will be less when voltage V in the power expression P is equal to VI. Voltage will be high, power has to be low, current has to be low. So that's why. So the current is low. Again, the same question. What is the advantage? The voltage can be changed. Advantage of using an AC current is that we can use the AC current. That is the requirement for a transformer to work. That's why. So when we move this magnet, what is happening? An EMF is inducing. Once you move it in and out, there will be like needle will be going like this and this, and the speed by which you move in and out gives you the amplitude of the EMF and the current as well. So when you fastly move it, that means you're increasing the amplitude. Pushing the magnet faster will increase the size of this reading here on the ammeter. This question, so we have a transformer input voltage, output voltage. So we have the resistor and voltage gives us the current flowing through here. And then this current will be used in this relationship to calculate the current here. Once you got both the currents, you can just calculate the power anywhere. So this is how it's been worked out. Look at this carefully. First, we calculated the current here using this. V1 over V2 is equal to I2 over I1. And once we got the current, now multiplying voltage with current gives us the powers. So why we use a split ring commutator? Well, it changes the direction of the current in the coil as the coil passes the vertical position, and that is this gap here. That makes it a split, and it's a carbon ring. Sorry, it's a copper ring. So, which diagram shows the voltage output of an AC generator? It's this one. It's always this one because it completes positive half cycle, and then negative half cycle, and then mean position. And this is what happens when one complete rotation has taken place. So you move the magnet into the coil. What does not produce an increase in the reading? If you increase the resistance of the ammeter, that has nothing to do. Everything else, you increase the number of turns, it will increase the reading, increase the speed, will increase the reading, strength of the magnet will increase the reading. Thank you. So, this is a motor. The labeled part is a, which one? It's D. D is the commutator. So, transformer question. First, we have to calculate the P in and P out, and then the efficiency. So P in is 25, P out 24, efficiency 0.96, given in choice C. Speed of the rotation of an AC generator is given by this curve. If we steadily increase the speed, which graph shows? So steadily increasing means you have to make sure the frequency doesn't change. Okay, so you increase just the speed, not the frequency. So for the same 0.5, look at 0.5 no, 0.5 no, 0.5 no, 0.5. Well, now you're increasing the speed. So you're here increasing the speed, the amplitude is increasing. The core of transformer uses iron because it is easy to magnetize and demagnetize, makes it possible to induce the voltage in the primary. current is produced when you move the coil, that's a generator. Why we need a transformer? Because we want to step up the voltage to reduce the power loss and decrease the current. Bar magnet is pushed, reading shown. Magnitude of the deflection is the speed with which the magnet enters the coil. We have done this. The output of a simple AC generator is this curve, always this curve. Bar magnet is moved in and out. What is at X? And when it is out. So when the magnet is going in, there will be an N pole at X because it is opposing the magnet that is producing the EMF. The coil is opposing the magnet's poles. So coil becomes magnetized but opposed to the magnet's poles, N. When it goes out, it will be S because that's what when the magnet goes out, the pole on N will still be N, but the pole here will be S. So when it goes out, the coil wants to attract it. Coil again wants to oppose the change, causing it. Lenz's law. Which graph represents the new output when speed is doubled? So when the speed is doubled, the amplitude should be doubled. And so does the frequency. So frequency and amplitude is doubled here. What produces a higher rating? So moving a magnet, faster speed increases the reading. Three factors, remember there are three factors that increase the AC output magnitude. First of all, speed of the movement. Secondly, stronger magnet. Thirdly, number of turns in the coil. Number 19, each box is 5 milliseconds. Each box is 5 milliseconds. So if you have a complete one rotation, what is the time? So 5, 10, 15, 20 milliseconds. Does not depend on the resistance. We've done this before. While at vertical position, the EMF is 0, and that is shown by this. Which device provides an AC current output? Okay, we have here we have here splitting, and we have here the rotating magnetic field and the coil. So this and this will provide AC current, and this will provide DC current once movement is done. So the magnet is allowed to fall through the coil. When the magnet moves through the coil, the galvanometer shows reading to the right. And obviously when it will come out, the reading will be on the left. Why? Because of the interaction, this EMF due to the magnet. Here it is in one direction, and then here the poles have changed. Here there are different poles, so it shows the direction in the opposite side. When we have a quick movement, the direction of current is reversed because we are taking it out, pulling it out. So we are reversing the direction. And because we are moving it quickly, the speed is increased, so the size of the EMF will increase as well. So B is false. So which statement is correct? Let's rule out the wrong ones. The direction of potential difference is always the same. No, because it will change because this is an alternating current generator. Size of inducer does not change as the coil rotates. It does change. It increases, increases. Winding makes no difference. It does because more winding means more current. The size of induced EMF depends on the number of turns on the coil. Yes, because the number of turns will increase the number. Sorry, the last one, the winding the coil on a soft iron makes no difference. It does make a difference. It does not, well, winding the current on the soft iron makes no difference. No, it does make difference. So this is the only correct option, that if you increase the number of turns, you increase the EMF. Same, but different question. So some changes are made one at a time, which increase the EMF. So if you just look at all four, except the last one, all three will do. C is the choice. So twice of the original output will be this, but this one should be with increased amplitude. Twice of the original output at twice the speed. So speed increase means amplitude increase and also the frequency increase as well. Why is electrical energy usually transmitted at high voltage? Because we want to waste as less as possible voltage, power or energy. Number 29. Magnet is pushed horizontally, induces an EMF. The EMF, which direction does the EMF makes the coil move? It wants to move away from the magnet. Why is this? Read about Lenz's law. The EMF produced in the coil is such that it induces poles onto the coil, and the poles are such that they oppose the reason causing it. So magnet is the reason causing the poles, so they will induce opposite poles of the magnets, this pole. When we have two opposite poles, the force, the repulsion force between them will push the coil this side. So it will be away from the magnet. So we have a generator, coil rotates 20 times in 1 second. So if you look at the 20, you have 0.05 second time. 1 over 20 gives you 0.05. Remember, it's the frequency and time period relationship. F is equal to 1 over T. So T is equal to 1 over F. F is 20. So T will be 0.05. Now, which of these will be 10 times, 10 frequency of 10? It will be this one, the half of that. To increase the voltage and decrease the current. Yes, the connector might be moving too slowly. That's why no deflection is seen. Why A, C, and D are wrong? Well, the ammeter is not between the poles. It doesn't have to be. Connector is not cutting the field lines. Well, as long as there is a vertical field and you have horizontal movement, either this way or this way anyway, but obviously movement is shown in this way, so it is cutting. Poles are too close, and that doesn't really matter. Very simple. These two transformers will produce step up, these two step down. This transformer, we have a DC input, it's not going to work. We need an AC current, AC voltage. This transformer will produce the larger output than the input. Simple AC generator voltage waveform is this, always. Well, the input voltage is less than the output voltage. Very simple, straightforward answer. Which of these will increase the reading on the ammeter? Let's go through all of them. Move the coil slowly, no. Put the resistor, no. Turn the magnet round, no. Use a coil with more turns, yes. So when the magnet moves through the coil, first the deflection is on the right side. When it goes away, due to the Lenz's law, the deflection will be left side. And then once it's gone down, the deflection will go back to zero. So this transformer at X increases the voltage and decreases the current. And then the voltage is transmitted across the long distances. So which factor will increase, would decrease the maximum value of the EMF? If you raise the support of the spring, that will make it far from the coil and less EMF will be induced. All others, while raising the coil will actually increase it. Increasing the strength, magnet will increase. Increasing the number of coils will also increase. So, which graph shows the voltage is increased? Output voltage is this one because we have increased the. So look at the question. Same scale shows the output voltage varies with time at the same scale. So it's this one. Transformer has more turns on the secondary, so the output voltage amplitude should be more. So how the wire should move to produce? Well, it should move up and down. Here's an axis. Actually, it is a motor. So when we have AC supply, the supply will be switching, the direction of current will be first coming this way and then coming this way. So if once the coil is moving up, the other half cycle coil will be moving down, so it will be moving up and down. So it has 4 times each second, and 4 times each second is the frequency 4. That should give you the time 1 over 4. So 1 over 4 means in 1 second, we can just have a look. Why it is here? So we have 1 and 2 completed in 0.5 seconds. So 1 will be completed in 0.25 seconds, and that's the time period. If you have the frequency 4, the time period will be 1 over 4, i.e. 0.25. So this one is the correct match. Transformer, an EMF is induced in the secondary coil when alternating current is applied in the primary coil. All others are wrong. Let's look at them. Why? EMF induced in the secondary coil is steady current. It doesn't work on steady current. Current in the secondary is always larger. No, it doesn't have to be. The voltage always larger. No, it doesn't have to be. What is not a valid reason for transmitting an energy at high voltages is that a high voltage is safer than a direct current? No, that's not a choice. Why can birds stand on overhead high voltage transmission line without suffering any harm? Because, well, they are not connected to earth, so one might also say that their feet are good insulators. Both are possible. So this time it is given as B. It can also be Bravo as well. Because so many times they die as well. 100% efficient, input voltage 3, output 2 amps. Use these conditions, what output voltage and current could be obtained? So 100% efficient. So you have to worry about which one gives you the same power. So we have the power at the input is 6. Power at the output should also be 6. The only choice is D. 6 times 1 is 6. Pushes the N pole, the end Q, and there is a deflection. Pushing the S pole into P will produce the same deflection. So we have 240 volts, 12 volt, 240 volts to 12 volts step down, and there are 600 turns. The guy wants to know the primary, the turns on the primary. We just use this relationship. It comes out to be 30. It's because we want to reduce heat loss from the power line. So this question, we want to see what output voltage will be, which coil, how many turns of the coil will give us the 12 volts from the 6 volts stepping up. So first of all, a very quick knowledge check. It's a stepping up, so it should have more turns in the secondary. The only option is 40, but we will verify this. Look at this relationship, comes out to be 12. So yes, it will be 12 volts, R and S. Between R and S, the only option that gives you 12 volts. So we have a magnet and it's suspended and it moves like a pendulum in this, we have a conductor moving in the magnetic field like a pendulum. Each time it takes one complete revolution or oscillation, there is an EMF, whose cycle is completed, and that is given in this graph. One complete oscillation will give you this curve of the EMF. To reduce loss of energy, N falling through the coil, galvanometer shows the reading. When it falls away, galvanometer deflects to the left. Here,